This is the Science Fair Electronic Digital Logic Lab Kit. It was new for 1978, as we can see in this page from the Radio Shack catalogue. In the US, it retailed for $12.95, and in the UK for £7.95. Unfortunately, for its launch in the 78 catalogue, it was only printed in black and white. However, that doesn't matter, because of course here we have the kit in full living colour. On the front of the box, it says there are 25 experiments in digital logic circuitry. And if we look along the front here, we can see that the kit is a great introduction to digital logic circuits. It includes experiments with AND, NAND, OR, and NOR circuits, and it includes an IC, some LEDs, and all required components. It does require 3 AA batteries, which I've already installed, and as it says here, it was manufactured in Taiwan for Radio Shack, a division of Tandy Corp. So let's open the box and take a closer look. As is typical with science fair products of this type, the kit includes a large, nicely printed manual. We'll take a closer look at that in a moment. We also get a bag of wires, and now we can see all of the components installed on the cardboard base. This kit is designed to continue to live inside the cardboard box, and so I'm going to leave it in place. As you can see, there are a variety of components, including 8 resistors, 8 capacitors, 3 keys for input, 2 battery receptacles, one for 1 AA and one for 2 AA batteries, 2 LEDs with current limiting resistors, and an integrated circuit. The integrated circuit at the centre is a Texas Instruments SN7400 Quadruple 2-input Positive NAND Gate. The 7400 is the first of the 74 series of integrated logic circuits. Here I have the very brief datasheet for the 7400. The first page contains details about transistor-transistor logic in the 74 series. This includes things like the maximum voltage and the maximum operating temperature. It also includes how the circuits can be connected together. Here we can see more details specific to the 7400 itself. This includes the pinout in the 2 form factors that were then available. We have the form factor on the right. This shows us which pins are connected to which gates. It details what each gate does in positive logic, that is Y equals not A times B, and the manufacturer kindly provides a schematic for each gate in the circuit. We'll come back to that later. The subtitle for the kit is Experiments in Computer Circuitry, and if you've seen any of my other videos about basic computational devices, you know the first thing I want to build is a binary counter. If all goes well, by the end of this video, we'll have just such a binary counter based around this very chip. But for now, let's take a brief look at the manual. We start off with details about early computation. Then we have some examples of computer systems, including a photo of a chip from National Semiconductor. This is the SCMP microprocessor, often known as the SCAMP. We have details about the components in the kit, an overview of a NAND gate, and then an introduction to combinational logic circuits. We then start progressing through the experiments. Here it starts off with light-emitting diodes. However, as the kit is based around a NAND gate, I thought it'd be fun to start looking at a NAND circuit. So, I'm going to jump ahead and start looking at circuit number 9, the 2-input NAND gate. The instructions show a full wiring diagram, the wiring sequence, and a schematic for the circuit. So let's wire this together and see how it works. As we made that last connection, the LED illuminated. Let's look at the truth table and see what happens when we press the A and B keys. If A and B are both open, then the LED is on. If A is open and B is closed, the LED remains on. If A is closed and B remains open, the LED remains on. And if both A and B are closed, the LED extinguishes. The manual provides areas where we can write down the outcomes on the truth table. Fortunately, I don't have to go to that trouble, as I've gone ahead and printed out a cheat sheet of logic gates from the UK's National Cybersecurity Centre. In the bottom left, we see the NAND gate. Earlier in the video, I mentioned that Texas Instruments provides the schematic for each of the gates in the 7400 in the datasheet. That means we can go ahead and actually build our own NAND gates following the same circuit design. Here is a breadboard recreation of that circuit. In the schematic, we can see a transistor with two emitters. I don't have such a transistor, so what I've done is parallel together the base and collector of two transistors here to have the same effect. On the right-hand side of the schematic, we can see the output stages. And here that's comprised of three transistors and a diode, and essentially in the same layout and design that we see in the schematic. I have had to tweak the resistor values very slightly to account for availability and the exact types of transistors I'm using in the breadboard. So let me add some wires so we can test this circuit out. I've put the wires into the correct place on this breadboard. We have a red wire for power and a black wire for ground. We have the A and B inputs and the Y output. So let's take the IC out of the circuit, put this NAND gate in instead, and see if the circuit behaves the same way. As you can see, when I made the final connection, the LED again illuminated. So let's check the operation. When both key A and key B are open, we should see an output of 1, and we do. When key A is open but key B is closed, we should still see an output of 1, and we do. When key A is closed and key B is open, we should still see an output of 1, and we do. And when we close both A and B, we should see an output of 0, and the LED has extinguished. So this breadboard NAND gate is equivalent to the one inside the chip. While I could probably make the breadboard layout slightly more compact, the IC is a far more space-efficient way of packing circuits in together. The NAND gate is what's known as a universal gate, and that means it can be used to construct any other kind of logic gate. The NAND gate, or NOT AND gate, is the inverse of the AND gate. All that means is that everywhere we see a 0 in the output for an AND gate, we expect to see a 1 in the output for a NAND gate. And everywhere we see a 1, we expect to see a 0. So if we want to get back to an AND gate, that means everywhere we see a 1 in the output, we need to replace it with a 0, and everywhere we see a 0, we need to replace it with a 1. We can do that with a NOT gate or an inverter. Fortunately, the Digital Logic Lab includes just such a circuit, so let's tidy this away and try to make the IC inverter. The X LED indicates the input state, and the Y LED indicates the output state. Because key A is open, the input is off, and so the X LED is not illuminated. The inverter turns this logic low into a logic high, so the Y LED is illuminated. If the X LED is off, the Y LED is on, and if the X LED is on, the Y LED should be off. We can test that by closing the A key. As you can see, now the X LED is on, the Y LED is off, and when I release the key, the LEDs will invert again. To convert the NAND gate to an inverter, all we had to do was connect both of the inputs, as you can see right here. If we look again at the cheat sheet, this makes a lot of sense, because if we connect both inputs together, there are only two possible states for a NAND gate. Either both inputs are 0, which results in an output of 1, or both inputs are 1, which results in an output of 0. As we can see, this is exactly what we'd expect from an inverter. An input of 0, an output of 1, an input of 1, and an output of 0. So let's try combining these two gates, a NAND gate and an inverter, to create a regular AND gate. So now we've wired up our AND gate, let's check the operation. If A is open and B is open, we expect the LED to remain off. If A is open but B is closed, we still expect the LED to remain off. If A is closed but B is open, we still expect the LED to remain off. But if A is closed and B is closed, then we expect the LED to illuminate. An input of 1 and an input of 1 results in an output of 1. In all other circumstances, we expect a logic low or an output of 0. So now I've shown you a few different ways you can combine NAND gates to create other types of logic gates. And there are many more examples in the provided lab manual. However, earlier in the video, I said I was going to try and create a binary counter. While there are many ways to achieve a binary counter using logic gates, in the spirit of experiments in computer circuitry, I thought it'd be interesting to think about how computers add numbers together. When you think about it, a counter simply takes the previous number and adds 1 to it. 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, and so forth. For now, let's start simple and think about adding 1-bit binary numbers. If we only have 1 bit available for A and 1 bit available for B, these are all the combinations we can come up with. When we add A and B together, we get the value in the sum column. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 2. In binary, we can only represent numbers using 1s and 0s. So to represent a 2, we put a 0 in the 1s column and a 1 in the 2s column, which gives us 1, 0. But for now, let's ignore that special case. If we only consider the right-hand column of the sum and compare that with the logic gates from the cheat sheet, we'll notice that one of the gates already meets our requirements. That gate is the XOR. Here we can see for an input of 0 and 0, we should get a 0. For an input of 0 and 1, we should get a 1. For an input of 1 and 0, we should get a 1. And for an input of 1 and 1, we should get a 0. Again, we'll handle that special carry case later. Fortunately, the manual tells us exactly how we should construct our XOR or exclusive OR circuit using our NAND gates. So let's check the operation of our exclusive OR gate. For 0 and 0, we should see an output of 0, which looks good. For 0 and 1, we should see an output of 1, which also looks good. For an input of 1 and an input of 0, we should see an output of 1, which also looks good. And for an input of 1 and an input of 1, we should see an output of 0, which also looks good. So our XOR gate is working correctly. However, 1 plus 1 isn't 0, so we need to do something for that special case. As we can see on the reference sheet, this special case only occurs when A and B are 1. So if we look at just the left-hand column of the sum, we should be able to find another gate that meets our requirements. That gate is the AND gate. Only when both inputs are 1 is the output 1. To create an AND gate, all we need to do is build an inverter and connect it to an existing NAND gate. If we look on the schematic just here, we already have a NAND gate that's combining the values from A and B. If we want to turn this into an AND gate, all we need to do is take the output of this first NAND gate and put it through an inverter. We know we can make an inverter with just one NAND gate. Sadly, there are only 4 NAND gates in the 7400 IC included with the kit. Fortunately, as we've already seen, I've created an additional NAND gate on this breadboard here. So let's wire it as an inverter and connect it to the circuit. All I've done is connect both inputs of our new NAND gate to the output of the first NAND gate inside the IC. The output of our new NAND gate then goes to the Y LED, and I've added an additional wire to the Y LED to complete the circuit. So let's test out our 1-bit binary adder, but bear in mind that X is the right column of the sum and Y is the left column of the sum. So for the inputs of 0 and 0, we should get a sum of 0, and neither of the LEDs are illuminated, so that looks good. For an input of A0 and B1, we should get an output of 1, and our X LED illuminates, which represents the right-hand column, or a 1. For an A input of 1 and a B input of 0, we expect an output of 1, and again the X illuminates, indicating the correct response. Finally, for an input of A1 and B1, we expect an output of 1, 0, representing a 2. If we recall that Y is the left-hand column and X is the right-hand column, we do indeed get 1 and 0, so this is all working correctly. The circuit we've just built is known as a half adder. If we want to add larger numbers, such as 2-bit binary numbers, we're going to need to extend that circuit. To extend the adder, we're going to need more NAND gates. So for that reason, I've recreated the XOR circuit on the left-hand side of this breadboard. I've also created 2 more copies of the XOR circuit on the right-hand side of the breadboard. So let's see how these circuits connect together to create a more complicated adder. On the left-hand side here, we have the basic XOR circuit. That means I can press A1 and get a 1, or B1 and get a 1, but if I press both together, I don't get any carry. That's because I'm still missing the extra NAND gate that we're currently using in the Digital Logic Lab kit. So let's borrow that and see if we can fix the problem. For now, let's use the existing LED in the kit just here. For that, I'm going to replace this wire here with a longer wire like so. A1, B1, A1 and B1. And you can see that we have this LED here illuminating. Now we need to extend that output into the next stage of the adder. On the right-hand side are 2 more XOR circuits, and they've been connected together to form the basis of a full adder. A full adder allows an input from a previous stage to be carried in. This works by taking the combined output of the first stage and taking it into a second XOR circuit, where we can then add an additional carry in bit. So let's remove that long green wire and instead have the carry go into this second stage of the adder. Now we can add 1 plus 1 and get 2. We can also, of course, add other values, 1 plus 2 to get 3, 2 plus 1 to get 3, and we can even try 2 plus 2. But that's where we see the next problem. As you can see, that would be a 4, but we don't have an LED for that position. This full adder is actually still incomplete. It requires another NAND gate to handle the combination that would result in a carry into the next stage. But for now, I think a 2-bit input and a 2-bit output is more than enough. To create a binary counter, it would be handy to be able to store the data so we don't have to remember what we need to add 1 to create the next value. The user manual does include some examples of data storage circuits, such as this gated RS flip-flop, also known as an SR flip-flop. Unfortunately, this circuit requires both a set and reset signal, and our adder only has 1 output for each bit stage. Of course, we could create some more inverters to create the relevant signals. However, there are some other circuits we could consider. I've gone ahead and modified the gated RS flip-flop into the gated D-latch. Like the RS flip-flop, the D-latch allows us to store 1 bit of data. But unlike the flip-flop, we only require a single data input just here. So let's clear this all away, build the circuit, and see how it works. The A key provides the data input, and the B key gates whether or not we should store the data. If we press the A key, nothing happens. However, if we press and hold the B key, we can then tap the A key and it will change the state of the data latch. Whatever state we're in when we let go of the B key will be stored by the data latch. In our binary counter, we're going to use the D latch to store some data. We'll then process it with the adder and return it to the D latch. A simple way of testing this is to use the inverter as the data processor. A 0 on the output should be turned into a 1, and a 1 on the output should be turned into a 0. So let's connect the inverter and see what happens. What I've done here is connect the input from our inverter to the output stage which powers the LED. I've connected the output of our inverter through to the switch, so I no longer have to press key A, the data input. Like before, nothing will happen until we press the B switch. As you can see, that seems really unreliable. When the B key is closed, this circuit creates a constant feedback loop. That means the output is not determined by how many times I press the switch, but rather which state the circuit was in when I released the key. As you can see, the circuit seems to prefer the Y output, so let's take a closer look and see what that might be. Using an oscilloscope, we can better understand what's happening in the circuit when we use an inverter to take the output from the D-latch and pass it back in as an input. If I press the B key to enable the latch, we can see two traces on the display. The top trace is connected to the X signal, and the bottom trace to the Y signal. Although it looks like the X signal is always off, on the display we can clearly see there are brief periods where that signal goes high. Conversely, the Y signal spends most of its time in the on state and only a brief period in the off state. These two signals are essentially the inverse of each other. The time base is currently set to 100 nanoseconds, and that means each division on the screen is 100 nanoseconds. Although I don't think the divisions will come across very clearly on the video, I can count 1, 2, 3, 4.5 divisions between the signal pulses. That indicates that each signal pulse is 450 nanoseconds or so. That means that these signals are flashing on and off at approximately 2.2 megahertz. Because of the extremely brief period that X is enabled, that means that X looks like it's always off, and Y looks like it's always on. To solve this problem, we need the circuit to act only once every time we activate the gate switch. One solution is to combine two D-latches together with an inverter into a D flip-flop. I've prepared two D flip-flops on this breadboard here, so let's take a closer look and see how they work. Just like in the Digital Logic Lab, I have a D-latch right here. If I press the data switch, nothing will happen, unless I'm holding down the enable key. You'll notice that both of these D-latches are acting together, and that's because the output from the first D-latch is coupled to the input of the second D-latch. To make them sequential, we need to invert the enable signal between the two D-latches. Now when I press the enable button, I can configure the first D-latch as much as I like. Only when I release the key will that value be copied into the second D-latch. Together, these two D-latches now represent a single D flip-flop. So for that reason, I'm going to remove this LED to avoid confusion. Now data will only be stored when we release the enable key. Together, these four ICs represent 2 bits of data storage that we can use in our binary counter. The last thing we need is some way of sequencing the logic, and for that we're going to need a clock. Fortunately, the Digital Logic Lab includes an astable multivibrator circuit that will be suitable for our purposes. So let's clean this away and build the clock circuit. As you can see, LED X and LED Y are now flashing alternately. However, if you look closely, you might notice that they fade in and out. That's because this circuit is now dependent on the analog characteristics of the capacitors that determine the frequency. We can clean the signal up by using an inverter. Unfortunately, there are a couple of spare gates right there on the IC. So now I've cleaned up the signal for X, and hopefully you can see that the LED is much more decisive in turning off and on again. As X will be the enable signal for our data storage, we're also going to need the inverse of that signal for our D flip-flops. So let's go ahead and use up the last NAND gate in this IC and create another inverter. So there we have it, a much more decisive clock signal. So let's finish up and connect everything together. First, let's wire up the memory board and add some power. Now, we actually have primary and secondary phase clock signal, so we won't need this inverter here anymore. So let's connect up the clock. Next, we need our adder board, but of course we previously removed the inverter required to handle the carry, so let's add that back again. And again, connect the power. And the carry now works as well. Let's now connect the data from the adder into the memory. And finally, let's connect the output of the memory into the B inputs on the adder. So we now have a complete binary counter, and we can control the A inputs to determine how the binary counter operates. If I hold down the 1 button here, we'll see that it counts sequentially. We can see the output on the memory just here, and we can see it go through from 0, 1, 2, 3, 0, 1, 2, 3. And that works perfectly well. Because of the way this works, we could also have it count down. If we hold down both of these buttons here, we can see it will count down instead. 3, 2, 1, 0, 3, 2, 1, 0. And of course, we don't necessarily need to hold the buttons at all. I could install a small jumper wire here to act as shorting this button out. And now the binary counter works entirely on its own. In building a binary counter from an adder, we've actually constructed much of the circuitry required to build a computer. For a general purpose computer, you would indeed need more circuitry, but the adder provides the basis for an ALU, and the memory board represents a single register that could be expanded to large amounts of memory. A more general purpose computer would have a program counter, a special register indicating which instruction to execute next. It would also have some kind of instruction decoding. But our adder already implicitly understands two different instructions, increment and decrement. And there would be need for other types of control circuitry, including things like memory management and multiplexers to allow us to select between different data sources. Nonetheless, these are all things we can achieve using a NAND gate. It is, after all, a universal gate. However, this video has already taken quite a deep dive. We started with NAND gates and looked at how they can be built from transistors. We looked at how they could be combined to form memory and even do basic computation in the form of this adder. But if you're looking for more basic computation, do look out for my video on the Digicomp 1, which is a mechanical binary computer, in which I also construct a binary counter. And if that's not enough, why not consider my video on the Science Fair Digital Computer Kit? In that video, we look at constructing a binary counter, this time using nothing but switches, and we talk about how switch optimization was fundamental to early relay-based computers. But for now, I hope you found this video interesting, and I hope to speak to you again soon in the next one.